So yeah, I'm based here in Pittsburgh. I lead the brain team presence in Pittsburgh, and I'll be talking a little bit about Vizier, which is a project on black box optimization and AutoML. And I'll be talking about the work of the whole team here, so it's not just me. All right, so what is black box optimization? So it's called black box optimization because you presume that you have some kind of function, right, of some known parameters or knobs, and you can't really peer inside this system. So you want to find the best settings of these knobs, but the only way you can actually figure out how good they are is to actually set the knobs appropriately and run some kind of experiment or process, which is considered quite expensive. Then you run this process, you get back some kind of objective value, like some performance measure, right? And then you want to try to find the best settings of these knobs. But the system is relatively opaque, right? And so you have a relatively small budget of evaluations. You can think of this as maybe only a few dozen or maybe a few thousand, but not like millions or billions typically. And you want to try to do the best job that you can. And this becomes quite prevalent in the real world because as systems grow more and more complex, oftentimes even if you actually can model them, like they're systems created in code, for example, and you can actually inspect how they work, they can still be quite difficult to understand. And then there are other kinds of systems where it's just, they're just too complex. And this is essentially the only way you can interact with them. So in particular, we don't assume much about this function. It's not necessarily concave or smooth or anything like that. And it might have many, many local optima. We want to kind of avoid those and go for the global optima. So that is the kind of framework for black box optimization. Because we make so few assumptions about the objective function we wish to optimize, there are actually a wide range of applications that fit into this framework. So here are 4 application domains that I've highlighted here, and much of the work we do is around these. So for example, you can imagine you parameterizing some UI or UX and actually do automated A/B testing on websites, right? Various people will, when they're designing websites, say they want to change some aspect of it, do some A/B experiment, measure the user reaction in some way, and try to figure out which design is better, right? And you might want to try to find the best design within some space, and you can use black box optimization to do that. Another kind of application is in the machine learning space. Many machine learning models, or virtually all of them, have these hyperparameters, which are parameters that can strongly affect the performance of your model, but you cannot learn them directly during training. You have to sort of set them in advance. And this is another example where the black box here is you set these parameters, you run training, you evaluate your data, you evaluate your model on some test set, for example, and then you want to try to get the best performance. That can be formulated as a black box optimization problem. AutoML as well, like architecture selection for a deep learning model, that is also an example of black box optimization here. Right. There are other problems where you have just physical design problems, where you want to optimize some process or physical design, and perhaps you try to optimize it in simulation or in reality. I'll be talking a little bit about one where we're interested in optimizing chocolate chip cookies for taste, right? And that's one where you can't even know yourself what makes the chocolate chip cookie good for you, right? Like you don't even have a great model of if I gave you 2 chocolate chip cookie recipes, if I were to bake these and feed them to you, which one would you prefer? It's actually very difficult for you to evaluate that without just baking them and eating them with any sort of precision. So this is an example where you just cannot open up the box, right? And there are other applications in robotics for optimizing your robotic control policies, for example, to say like how the robot moves in order to do things like make the robot move efficiently and minimize jerkiness so you don't damage the robot and so on. So those are some example domains. So a while back we set out to build a service for black box optimization. We gave it this name Vizier, which is a royal advisor. Right? It sort of recommends what to do for you. And the design goals here, we wanted a system that would be really easy to use for clients because the easier it is to use, the more people will use it. And it's not really useful to build something that nobody uses. We want it to be reliable because, again, if it's not reliable, it's not highly available, people won't depend on it and they won't want to use it. We want it to be scalable for the same reason. We wanted it to be able to support state-of-the-art algorithms and allow us to investigate lots of new algorithms, to be sort of flexible and support research. in a wide range of applications. So these are the 5 main design goals we set out. Some of these are kind of in tension with each other. So if you build systems, you might realize that having something that's really easy to use and that's really flexible, these things are often in tension, right? Similarly, something that supports state-of-the-art algorithms, but is also really reliable and scalable, these can be in tension, right? If you're constantly modifying the system or constantly tweaking it. But I'll tell you a little bit about kind of how we went going about building this and what it actually means in terms of each of these design goals. So ease of use, we built it with minimal configuration in mind. You just specify a study name, what parameters you want to optimize, various access control lists if need be, if you want to keep your data private. And the client workflow is very simple. You just register a study with some parameters, and then you can just repeatedly go through this workflow where you ask for a trial with parameters to evaluate it, run it, which is application-dependent notion of evaluating this set of parameters, and reporting back, and then you report back results. We have clients in Python, C++, Golang, and Java, and a web front end, and an integration with Colaboratory, which if you haven't used it is very similar to Jupyter Notebooks. So it's really easy to use. For scalability, we built it as kind of a microservice architecture here. Evaluation workers, these are the ones that are evaluating these trials. They ask for trials from the Vizier API, which talks to some database and actually looks up any previously generated trials, or if new ones need to be created, it talks to the suggestion service, which is backed by replicated suggestion workers. The point is that the design is scalable to thousands of parallel evaluations in a given study. That is, you can be running thousands of trials simultaneously. You can have up to millions of trials per study and essentially unlimited studies. Right? We wanted to be able to support kind of all of the hyperparameter tuning at Google, and really ultimately like the global hyperparameter tuning workload. And this current design actually can support that. We want it to be very reliable, so we use kind of the standard practices around testing and monitoring, alerting, release processes, and so on. But kind of one interesting design aspect of the system that I would want to highlight, because I think it's quite interesting, is a lot of these. So for Vizier, we did not require that generating new trial suggestions be really fast, because the idea is you want to be able to spend, the trials are expensive to run, so you're willing to spend a little bit of time to compute very carefully what you should do next. And because of this, we actually represent the work as a token in the database itself, right? Like a request for a trial and when that's fulfilled. And what that allows you to do is you can actually allow the system to introspect and say, it's tried to generate a trial for this particular study, 5 times, and it's failed 5 times in a row, because maybe there's a bug in one of the algorithms that's servicing this study. Or some study has used up a whole bunch of quota, we should throttle it. And representing the work in the database in this way actually allows you to do this in a straightforward manner. So you get this nice introspection for free, and you can automatically kind of shut down or throttle or shut or disable problematic studies. And this has helped us quite a bit in the internal instance, so we use a lot for research purposes. As you can imagine, the internal research scientists really, they'll heavily leverage a tool like this and really press the limits. So we wanted to have state-of-the-art algorithms, right? And the suggestion workers are modular. We can support many different kinds of algorithms. So things like Gaussian process bandits and Bayesian optimization, sequential model-based algorithm configuration, it's called SMAC, evolutionary strategies like CMAES, older classics like simulated annealing, genetic algorithms, and then simple things like random search and grid search and other things. You might ask, well, okay, if you tried out all these algorithms, which are the best ones? This is kind of a natural question to ask. It's kind of interesting. There's an interesting challenge in evaluating algorithms for black box optimization, right? There are a few issues here. The cheapest thing you can do is come up with some analytic benchmarks and evaluate your algorithms against those. There are academic competitions where people actually do this, and various people come up with challenging functions. These are functions that are cheap to evaluate, but actually have like various kinds of properties. But the thing and these are like ones that I fit on this slide, for example, that have different kinds of characteristics in terms of some are well conditioned, some are ill conditioned, some have lots of local optima, some have few, and so on. But I do want to highlight here that there really is no perfect set of benchmarks. You know, if any of you are familiar with these no free lunch theorems, there's like these classic results that say you can't have like the optimal search algorithm for certain kinds of search problems. And kind of a corollary of that is there is no optimal algorithm for black box optimization. It really depends on what kinds of problems you're throwing the system at, right? So there might be an optimal algorithm for a particular distribution of problem instances, but in the real world you don't get that, right? Like the kinds of problems that people want to solve can change over time. So nevertheless, we still can use these algorithms to kind of cheaply evaluate things, and then we can do more expensive evaluations on real data sets and real kind of use cases for users. Let me tell you a bit more about a couple of these. So just to get a closer look, this function on the left is called Rosenbrock's banana function. It's called this because if you look at the level sets towards the optimum, it looks kind of like a banana. That's like this blue region. It's got an interesting property that it's kind of got this valley at the bottom that curves around. So let's say you're trying to minimize this function. It also has a nice property for our purposes here is that if you just run regular gradient descent on this function, it actually takes exponential time to reach the optimum. So the gradient descent doesn't do well kind of going around this nice like curved valley, right? But nevertheless, it's got this like one nicely connected, these connected sort of level sets, right? It doesn't have like lots and lots of local optima. Whereas the Restrigan function here on the right, it does have lots and lots of local optima, right? And so these are like two example kinds of functions that you might try to evaluate your black box optimizer on. Okay, so this slide, the details don't matter so much. The point to notice is that we run some benchmarks on like some 4-dimensional problems and some 32-dimensional problems with a few different algorithms, and like the ones that are best in 4 dimensions are different than the ones that are best in 32 dimensions, right? That's kind of the key point here. And this is not just some property of these particular algorithms, but it's a fairly general phenomenon. So another thing Vizier does is actually try to automatically detect characteristics of your problem and then select the best algorithm for those problem characteristics. Okay, so I wanted to just give you a bit of background to get an idea about what kinds of algorithms are used here. So I'll just tell you a bit more about 2 different approaches. Approach number 1 is Bayesian optimization. This is a very popular approach. It's in many ways the best approach that we know of in a fairly broad range of problem domains. Not all of them, but many of them. In this cartoon, we imagine that we have this one-dimensional one-dimensional parameter space, so one parameter optimize, and the objective function is plotted in the y-axis here, and we have some data points in green. The Bayesian optimization framework says that you should try to model the objective function, okay? So maybe this is the objective function, right? But you don't actually know that. It's hidden from you. And not only do you model the objective function, but you model your uncertainty in the objective function. So you try to come up with some sort of region that you believe that the objective function lives in this case shaded in blue here. And then once you do that, you have an explore-exploit trade-off, where you can try to select points that you believe are good with high probability, but are maybe not great, and other points that could be fantastic or could be terrible, but you have to sort of just try them to see, right? And there's sort of a trade-off here. And these are sort of fundamental. You can see this when you like choose a restaurant to go to. Do you go to like your favorite restaurant, or do you go to the new one that just opened up, right? Like, so exploiting would be going to the old restaurant that is your favorite one that's been open for a long time, and exploring would be trying the new restaurant. You know, because maybe you'll get a new favorite restaurant if the new one is really good. Anyway, here one standard strategy would be to find the maximum point in this upper envelope, right, this star here, and say, well, try the parameter corresponding to that next, right? So maybe you try that and you actually get this orange point because it's not so great, right? It's on this curve. And then you would just kind of update this picture, right, and then proceed. We use these Gaussian process models in order to model the functions. I mean, there are various other choices. Some people use Bayesian deep learning, and some people use kind of gradient boosted decision trees and other things. But the Gaussian processes are kind of state of the art for small data sets. If you don't know what these are, they're actually quite interesting mathematically. Essentially, it's a generalization of a multidimensional Gaussian, where if you imagine a multidimensional Gaussian, so let's say you want to model a function from a finite domain, like the integers 1 to n, to the real numbers. Well, then you can imagine identifying a value of this function with a vector of n dimensions, where the coefficients of that vector are just f evaluated 1, evaluated 2, and so on, right? So the ith coordinate would be f of I. Now you can imagine modeling a distribution over such functions with a multivariate Gaussian, right? And then Gaussian processes just generalize this to continuous domains. Like, that's what they are. So there are pros and cons. The pros are that these things are extremely flexible. They have analytic solutions for posterior inference, which is actually pretty impressive because it allows you to reason about these sort of infinite dimensional objects using finite amounts of computation. And they're really elegant, and they're amenable to some nice theoretical guarantees. The cons are that is that in naive implementation, they're extremely expensive computationally, something like n cubed, where you have n data points. The nice thing about black box optimization is you assume trials are expensive, so you don't actually have that many of them. So this actually becomes feasible. Okay, so that's one approach. Another kind of approach would be you just have some kind of simple probabilistic algorithm, right? Some authors have argued that just like random search works pretty well. I'm not sure I agree with that, but like here's a strategy that's slightly smarter than just random search, where you essentially pick new points using one of three strategies. One is you do some uniform random sampling. Another one is you take the best point you've seen so far, sample some ball around it, and pick a point in that ball, uniformly at random. This is like a sort of a gradient-free hill climbing. And another one is this linear combination sampling, where you create a new point via a linear combination of some older points. So why would you do this? Well, let's say you're optimizing this function. Here are the contour plots. The randomness allows you to sort of explore new areas and make sure you don't get stuck in some local optima. The ball sampling strategy allows you to kind of do this probabilistic hill climbing. So it works really well on well-conditioned objective functions, right? And it'll allow you to just kind of walk fairly efficiently to the nearest local optima. And the linear combination one, where you might have like these two red points and you sample this blue point as the new one, the new child point, that's nice for cases where you have really ill-conditioned objectives. So the conditioning here is kind of how much the function varies as you go in different directions. So a well-conditioned function, if you will change about the same speed no matter which direction you walk in. Whereas an ill-conditioned one, if you walk in one direction, it might look totally flat. And if you walk in another direction, it looks really steep. Right. Linear combination sampling strategy here is completely immune to ill-conditioned functions, actually. So you combine those three, and you get something that behaves quite well, actually. And there are a bunch of other algorithms as well. So in things like machine learning, like when you're optimizing machine learning models, you also have access to additional information. The black box assumption isn't completely true. Typically, as you're training a machine learning model, you get information about how it's doing as you train it for more and more epochs. So you can look at these curves of like performance versus time, or accuracy versus time. And that allows you to do things like automated early stopping, where if these are these training curves, and you see, you have a bunch of training curves that have completed, these solid lines here, and you see like this green dashed line, where you see this model, you can basically infer early that this model kind of stinks and you shouldn't bother finishing it, right? Whereas if you see this orange one that's sort of trending up, you say, well, it's doing worse than the other models were at that time, but it's got this weird trajectory that's very different than the other ones. So it might actually have some promise. Let's let it finish, right? So we have algorithms that will try to detect this and automatically decide which models to stop early to kind of save resources. Another type of algorithm here is you can do transfer learning, where if you run a study once and then you're going to run a similar study in the future, you can kind of use the data from your your previous study to accelerate your future study. This actually happens a lot in cases like machine learning, where people have a model and then they want to kind of add a feature, or maybe add a few features, and then rerun the model. Well, it turns out that the performance with respect to the hyperparameters will be similar. And so we use transfer learning to kind of zoom in on the good regions that were from prior studies. And one approach to this is to just kind of find good prior data and use that as a, and just model the residuals on top of that prior data. All right, so, but there's still room for improvement. So we did add what we call this algorithm playground, where we let kind of other engineers, essentially, and research scientists develop their own algorithms, and we can plug this into this playground binary and kind of substitute Vizier's production suggestion workers with this kind of binary, so that instead of our code suggesting what trials to do next, this kind of research code is doing so. And that allows us to experiment very rapidly, whereas from the rest of the workflow, it looks identical. From the evaluation workers don't have to worry about what algorithm is generating the trials. Okay, so we built this great system and we're thinking, how do we get people to know about it and use it? We're doing a pretty good job internally with the hyperparameter tuning, but we wanted to highlight some of these other use cases. So we decided, to go back to our roots. We're in Google Pittsburgh. This building used to be an Nabisco cookie factory. So we figured, why don't we optimize cookies? So we parameterize the space of cookies, right? Like what kind of chocolate to use, how much chocolate, how much sugar, white sugar, brown sugar, how much butter, how much flour, eggs, vanilla, baking soda. And then if you set these parameters, you get essentially a recipe. You can bake that recipe and then feed it to people and have them evaluate your cookies and then feed those scores back to Vizier and iterate, right? So in the third floor of this building, there's a cafe that actually has a teaching kitchen with something like 5 baking stations. So we took over that and started baking whatever Vizier told us to. So the cool thing about this is that you start with very simple ingredients. You can get extremely diverse cookies, right? So, and anyway, so we sort of went to town here. There were some surprises. So like, I don't know if you can see that so well, but this is a cookie where sort of Vizier went like maximize chocolate, basically like build a chocolate bar with a little bit of cookie dough on it, right? That was actually pretty well rated, but not exactly what we were looking for. So, but you can constrain the parameter ranges. Here's another one. Science does require sacrifices at times. So these cookies, this is what they look like when we scoop out the dough and put it on the baking pan, right? We used a kind of like an ice cream scoop, but a little bit smaller, all right? And then I took these out of the oven. Like I personally took these out of the oven, and they look like this, and I thought I had made a mistake. Like maybe like I thought they had been cooking for 13 minutes, but like they looked like completely raw. But it turned out they had been cooked, and we did feed them to people. They were not very good, but we did learn from this that like this is what happens if you have way too little butter, and the Vizier got better. So, and in the end, the results were definitely worth it. At first we used Chips Ahoy as a baseline when taste testing, because it's a pretty easy baseline to beat. But pretty soon we had to switch to using the classic Betty Crocker recipe, which is not such an easy baseline to beat. But we were pretty reliably beating that after about 40 trials, 40 different cookie recipes. All right, so in terms of the recipes, we have the optimal recipe here. There's a workshop paper, Bayesian optimization for a better dessert. You can look it up. Some high-level lessons learned. At least when you're feeding people who work in this office, your cookies should have less sugar and less butter than like typical recipes, and more chocolate, more salt, and a little bit of cayenne pepper. That was a lot of fun. It was a good test of the system because it tested noisy evaluation. We had infeasible trials. So like sometimes the dough came out was just too crumbly. You couldn't make cookies out of it. And Vizier does support infeasible trials. Configuration changes to unlock ingredients, manual overrides, because there might be human error in baking that we catch later, transfer learning when we adjusted the baking site. So we did the first sort of phase of this study here in Pittsburgh, and then when we had enough data, we actually scaled it up in Mountain View. So we took over the dessert commissaries there and started feeding experimental cookies to like 20,000 coworkers. So that was great. Yeah, come. Hmm? And yes, we didn't kill any of them, right? Yes, nice thing about Google, you can experiment on your coworkers and you don't need to even file an IRB. Yeah, so there was transfer learning involved, and it was a good test of our baking skills. You can actually use Vizier right now. It backs the hyperparameter tuning capabilities in the Google AI platform. It also backs many of the AutoML capabilities. I guess I'm running out of, I have like 1 minute left, so I did want to give people an opportunity for questions. Well, thank you.